Dasymetric mapping is one way that we can better focus and understand the idea of subunit variation. And it helps us to overcome the assumption of homogeneity in the distribution of geographic variables that are counted, observed, or reported in areas. And it's the use of what we call at least one ancillary data set. An ancillary data set means a data set that is used with your source data set to focus like a lens spatially where the thing that you're observing can or cannot be found in space. So it disaggregates coarse resolution data to a finer resolution. So it's a disaggregation technique. And this thing that you see on the right-hand side, or just the left-hand side, this little Ottawa thing, that's the population density in Ottawa. By only calculating population density where people can habit in space. And so you see a lot of it's gray. And this population density, of course, is very different from if we just used population density in larger regions like that we have as neighborhoods or as dissemination areas or census tracts in Ottawa or anywhere for that fact. So it's a way to focus the and tune the spatial configuration or the boundaries or add boundaries into the spatial configuration of source zones to distribute population or counts. When I say population, I mean a count of anything to get better results. Dasymetric mapping. Here's an example. So this is one dissemination area that we're looking at here, outlined in red. So the big thing outlined in red here. Just the red line there. That's the dissemination area. It has a count of 510 people. And the assumption of that 510 is that they're equally distributed all over this region. Now, I'm just pretending to draw out 510 individual dots in here where each dot is a person separated by enough space that each person, that there's an equal density across the whole region. Now, obviously, when I was doing that, you're thinking, well, why am I putting dots in fields and stuff like that? People don't live there, right? You're not allowed to live there in this little forest patch or this little bit of parkland here. You're just not allowed to do that. So people can't be everywhere within that area. So that means we can't have a homogeneous distribution of these 510 people in this space. And when we only have that data, this census data to work with, we don't know anything about the subunit variation in the environment that would be either conducive or non-conducive to where people could live in that space. And that's why we have that assumption. But with an ancillary data set, here, a remotely sensed image, I can delineate areas where people can or cannot live. So this is all commercial space up here. These are all stores on Innes Road in Orleans. And then I have there's some housing. This is all residential, and this little yellow area here. So there's one yellow area right there, and then there's another little yellow area over here where people can live, and then two smaller ones over here. And so those 510 people have to be allocated really to these yellow areas, the populated area of that zone or polygon. And the way I might do that, I might look at the area of each one. So paring it down to exactly where, and you can see this on the right better, the right-hand one, B, we have allocated 173 people to this part, 225 people to this part, and 85 people to this part, and 26 to this little part here. Now we have a very focused means by which to observe the population in space. We know how many people are in, or potentially how many people are in each one of these little yellow things. And we did it by looking at the area of each one. So we looked at the area of all the yellow things in total. And then we divided the individual areas of, let's say, A, B, C, and D, each by the total area to get a representative fraction, just like we do in basic area interpolation. And we multiply that by 510 for each of them. And that's how we got these people. Now, the assumption then still rolls back on us in that within each of these yellow polygons where people can habit, there's still the assumption that those people in there, like 226 in this one, are homogeneously distributed. You can't get away from that. But it's a much better spatial portrayal of where the people are than saying there's just 510 in this whole big zone that you see there. And so this ancillary data set was used to focus that population number and to disaggregate it within that region or zone to give us a better spatial picture. So binary dasymetric mapping is what I just did, or that's the process where I showed you a single ancillary layer, which says where people can and cannot live. That's why it's called binary, because our ancillary data simply delineates where things can or cannot be. Now, it assumes, just like everything, the assumption of binary dasymetric mapping is the homogeneous distribution assumption of the variable across subregions within source regions. And the target zone receives counts from the populated area of the source zone that are proportional, right, to the relative areas of the target zones that belong to the populated area of the source zone. That simply means that's what I was showing you a second ago, that I find the area of all the yellow ones together. That's the total yellow area. I divide each individual yellow area by that total to get an area ratio and multiply that by the 510. And that's the equation up here for doing that. This is the same equation as basic area interpolation. But it requires that you have a dasymetric step in that process for it to work properly. So let's see how this goes. So the basic procedure for creating a binary dasymetric map, or for binary dasymetric mapping, and the output will always be a map of the counts of some variables, is first, of course, we calculate and store the areas of the source zones. That's just called AIP here. And a intersects TP, intersect the source and targets, just like in basic area interpolation. And then multiply the total count in each source zone by the proportion of each target within the polygons that are being analyzed. Now, this equation has the requirement that you have a binary dasymetric map first, so that basically your source zones are clipped to the binary region. In other words, we'll see an example of. So when we say the equation requires that the source and target zones are prepared so that a given target zone intersects with at most one source zone. And the target zones are the regions that compose the populated areas of the source zones. That's the binary Dasymetric, or the binary map that is used in the process. And so we don't have a summation here in this particular case because we're bringing the data, or basically disaggregating data to a smaller geographic level with basic area interpolation through a binary Dasymetric mapping. So here's again another example. We have a region. There's 24 things, people, whatever in that region, and they're uniformly distributed. Then we have a binary layer. Here, these are the dark orange pieces. There's two dark orange regions here. And the first dark orange region is where people can live. The second one, also people can live. But people can't live out here, and they can't live over here. Let's say those are parklands or forests. So we then say, okay, of the populated area, so the total populated area right now are these two orange things together. And of the total populated area, 1/4 of this total populated area is down here, so that's the 1/4, and 3/4 are up here. So those are our representative fractions right here, are for basic area interpolation. So then we say 3/4 times 24 is 18, and 3/4 times 6, or times 20, 1/4 times 24 is 6. So that means in the end then, our new map looks like this. We have 24 up here, people, and 6 down here in the target geography, which is the same as the target zone in basic area interpolation. That can then become another feature. So once this is done and you've disaggregated the zone to subregions, those subregions can then become sources for another basic area interpolation to another geography. So let's look at an example right here. So there's that little region I was showing you before. So that's one polygon. And in that polygon, this dissemination area, there's 890 people. So that's the source zone. Below here is the source zones, all these source polygons, intersected with, directly with, a binary Dasymetric map. And so down here, anything that's gray, all these gray areas, people cannot live. And all we've done is transfer the values from the source zones to their parts. So that in this highlighted region, for example, there are 2 parts or sections. And we just call them 1 and 2 down here. And we find the total area of 1 plus 2. And then we intersect that total area, or we don't intersect, we intersect with its, we break it up and intersect it with itself. So this is what kind of this is showing here, that we basically find the total area and then we divide that total, the area of each of these 1 and 2s, so the 1 and 2 polygons right there, are divided by the total area to give us how much area is intersected here. So if you add these two together, 0.3 kilometers and 0.07 square kilometers, that gives you the total area of 1 and 2. And that's the intersected area. So these numbers for, let's say for 1 right here, that's this one right here, we divide that by the total. So we say 0.3054 by the total of those two small regions that now have the 890 count in each of them. And then we multiply that ratio by 890, and that gives us 717 people going into one. And we do the same for the small little 2 up there. That ends up with 173 people. And so that population now has been disaggregated to a much finer spatial scale with more detail. So preparing source and targets for binary dasymetric mapping. So we have some source zones, some source geography, and we want to spatially detail that or tune it or scale it down. Is another way of talking about that. That would be the more common way, would be scaling down aggregate data. So to scale that down. And so we have here a source, and then we have a binary dasymetric map. The binary map here is of populated areas, and this is just a section of Orleans. So we have a populated region, which is the orange. That's where people can live. Gray or anything else means they can't live there, and that's the ancillary data set. So we intersect our DAs, that's just dissemination area level, polygons, intersected with the binary dasymetric map, and then that equals one that looks like this. And all that's happening in this particular intersection is that, well, any part of the black binary mask that you see here that intersects any of the polygons over here, for example, will end up having the total amount, or the total that's in any of the DAs, assigned to each part that was cut up by the binary dasymetric map. And that's why over here you may see many more polygons. So the number of polygons is increasing. So that has a greater number. And each polygon has just had assigned to it the total population of whichever source polygon that it intersected. So now that we have this, that is the one that we have to now disaggregate to get the individual populations for each small part of the intersected polygons. So we intersect source and ancillary data. That's the first thing. So we take our Orleans DA and our Orleans zoning. So it's a zoning is, you can read about that. Zoning is what the city allows land uses to be within regions. So the zoning data is what you see right there, the black area, and that's just residential that was taken out, because it could be commercial, mixed residential, commercial, etc. So the mask was made from zoning data. And they're intersected to get just an intersected layer. And we call that new intersected layer the source, because that now becomes the source for basic area interpolation. So now we calculate the original source areas. So in our new table source, our new feature class, we get source area, add that field in as type double. Then we calculate geometry in there. So in the source table, we say source area field, and I chose area geodesic, just to show you how that affects the numbers when we do our validation at the end. And when you choose area geodesic, you have to choose the unit square meters and the coordinate system. I just took the current one that the layer was in, so I just chose the layer under there for that part. And again, you could just use at this step also, instead of that, add calculate field. So you could have just used calculate field here if you wanted to, and calculate the shape area over into source area. So here we have now the way it would look right now, basically after the intersection and source area calculation. This is one spatial unit. So the original DA is this, and that within that original DA, there were 1, 2, 3 separate parts of that DA where people could live. And each of these has assigned to it the population. So if the pop here of the original DA, that's the gray part, equals 10, well, 10 is here, 10 is here, and 10 is in that little sliver there. So what we have to do now at this point is to break apart these 3 polygons that are all the same color and have the same identifier, break them so that they have unique identifiers. And I just show that here with unique colors. There's a purple one, that's purple, blue, purple, blue, and turquoise. Then, for each of these, we now want to figure out how much each of these should get of the 10 people. Well, it depends on the relative areas. So we get the total area, which is already in here under source area. And we then divide the areas of each of these by the source area to get the area ratio. Let's say that, so it would be that. So that would be the turquoise area divided by source area times the 10 people equals the population for that particular polygon. Likewise, the purple area divided by the source area, which is the area of all 3 of them, times 10 would give how many people live here. And then same over here. So we'll end up with maybe 1 person here, 7 here, and maybe 3 here, or something like that, once we are completed the procedures. So now that we have the intersected, and that represents the one we already created, we have that and the source area calculated in there, we will do what's called a multi-part to single part tool. And that's a geometry tool that is the same as a region group in raster. So a region group in raster, the vector equivalent is multi-part to single part. And that will then break all these up into their individual polygons, and each one will retain the original source area, and each one already has assigned to it the counts from that source area. So the Dasymetric step now. For each of the target polygons, we calculate the new population counts by multiplying the source population value by the area ratio. That is the the exploded area, multi-part to single part, the single part area divided by the source area times the population. So we add a field to our targets table, and we call it BT, because that's the output field we want, which is population. And it's of type double, as usual. Then we calculate field. And in that new field, we're going to calculate the shape area divided by the source area times the population 2011, since that's what we're reallocating to these sub-units within each of the original dissemination areas. And that's in the BT field, right, that we created. Don't forget what field you choose. And that completes then the reallocation, or the Dasymetric map. To validate, well, it's the same type of thing as before. We would check the sum of the BT field in the target layer and the sum of the POP 2011 in the original dissemination area level data layer, and they should be the same. So the original dissemination area population sum is 106,830. The target area sum of the BT field is 106,824. So there's a 6-person difference here. And again, that's due to the use of geodesic area. That the way I did it, I used geodesic area as the calculation for source area, but only projected area in the shape area field, because it only shows the area as calculated in the current coordinate system for that feature class, which is a, in this case, a MTM9. And that's why we got the discrepancy here. So after doing it, this is how it looked originally. This is the original population density, if you looked at the dissemination areas only. And then the Dasymetric population density. And it looks quite different visually. For example, if you look at an area right here, maybe I'll make that yellow right there, and you compare that over here. This was very dark, had a high population density. Relatively high for this map here. But over here, it's, much smaller. And you'll also see that the absolute values of population density are very different, aren't they? And that's because of that area effect, right? Population density is people divided by area. And as we know, if area is larger, density is smaller. If area is smaller, density is larger. And so when we have smaller areas in which to compute population density, we get much larger values and more realistic values, in fact, of, what that area is like how would you run into a lot of people in some of these areas or not. So, in the yellow areas, be less people, but it's very dense, especially in this part here. And that's not so obvious when you look at the other one. It looks kind of dense in this whole region, but it's not as spatially accurate. Now, the Dasymetric map of population that we created right here, we could use that as a means to go with it as the source data for a basic area interpolation to a higher geography. So a more coarser level zonation. So this is the neighborhoods. So these are neighborhoods, ONS neighborhoods. And we'll get a more accurate transfer using basic area interpolation with this as the source area rather than just DAs, because these are much smaller than DAs. And so we've really got a spatially focused population. And this table just shows what that looks like. So here are the official numbers for these neighborhoods. And these are the neighborhoods right here. So the first one, for example, 8525 with just basic area interpolation, we get 8433. And with using this map here, the Dasymetric map to reallocate, we get 8444. So that's closer to 8525 than is the basic area interpolation from DAs alone. This other one is based on block, so the block population. So that's a very small level of geography. So it had the best performance there for that one. What about some of these larger ones? So there's an original 46240, 45934 with just basic area interpolation using DAs as the sources, and then 46247, much closer than 45934 with the Dasymetric here, and with just the blocks, not the Dasymetric, but the block level population, 45164. So we get the better performance there with that Dasymetric one. And you'll find if you look at these numbers that most of them give closer to the official numbers than just basic area interpolation or block source area interpolation with blocks as the source instead of DAs. And so this step, whenever you can do it, if you have to do some sort of basic area interpolation, think always, can I at least get a binary Dasymetric map to create a spatially focused, detailed population distribution, and then use that to go in the basic area interpolation process. And then what you've done is a binary Dasymetric map interpolation. The choice of aerial interpolation depends a lot on the data available and the analysis needs. For example, if you have no ancillary data, but you need to transfer attributes to new geography, then simple or basic area interpolation is your choice. If you have ancillary data, then binary Dasymetric map is your choice. You have no ancillary data, but you want to increase the spatial accuracy. Well, you can't, right? Because you have no ancillary data, so there's nothing in that one. If you want to increase spatial accuracy of a variable and you have ancillary data, then binary Dasymetric mapping again. So you could look at it that way as well. So this little table just gives a choice tool to figure out, when to use a binary Dasymetric mapping approach or a simple area interpolation approach. It depends on your needs, goals, and the data that you have available, particularly if you have ancillary data or not.